5 best practices for tools for creating seamless device control experience with Smart Home API. I'm Diane Lee, and I'm a Principal Program Manager on the Alexa Smart Home team. Over the last 5 years, we've worked with a lot of developers to build smart home skills, and based on what we've learned with working with you, we've put together this session to share some of the best practices and tools to use when creating a smart home skill. In this session, let's assume there's a company called Lighthouse Inc. that makes smart light bulbs. We'll be using Lighthouse Inc. as an example to illustrate the best practices for building a smart home skill and the tools you can use to improve the performance of your skill. So Lighthouse Inc. has created a smart home skill using the Smart Home API. The Smart Home API provides capability interfaces that enable you to describe your devices and properties, events, and directives that they support. In this case, Lighthouse Inc. has already implemented the power controller capability, which allows their users to use Alexa to turn on and off their light bulbs. This means Lighthouse Inc. has created a back-end implementation for their smart home skill, completed their account linking, and implemented a Lambda function to support the power controller capability. Now, let's assume that Lighthouse Inc. wants to allow their users to change the color with Alexa as well. The Smart Home API has a color controller capability that Lighthouse Inc. can implement to allow their users to change the color. For instance, users will be able to now use Alexa to set the color of their bulb to a variety of colors such as blue, red, or even salmon. We're going to use this example throughout the session and walk Lighthouse Inc. through their development of color controller and walk through some of the tools and best practices during their development. So through the session, we're going to walk through implementation of color controller to see if Lighthouse Inc. is sending the right response back to Alexa. We're going to walk Lighthouse Inc. through debugging to check if the device is changing to the right settings, and walk them through debugging the reported events they're sending to Alexa. We'll then walk Lighthouse Inc. through testing to see if they broke any other functionality. And lastly, we'll help Lighthouse Inc. manage and see how their skill is performing. So let's start with helping Lighthouse Inc. implement the Smart Home Capability Color Controller. Before we go into that, let us walk you through a high-level architecture of how Alexa works and processes a smart home capability. When a user says, "Alexa, turn the light blue," Alexa will process that utterance with our skill interaction model and trigger a directive to send to Lighthouse Inc. In this instance, Alexa will send a set color directive, and then Lighthouse Inc. will take that information that was given in the directive to control the device as the user requested. So in this case, Lighthouse Inc. will change the light to blue. Lighthouse Inc. will then send a response back to Alexa confirming that the light has changed in a response payload, and then Alexa will respond back to the user. So to implement color controller, Lighthouse Inc. will first update their Lambda to accept the color controller capability. This allows Alexa to send that set color directive request to Lighthouse Inc. Lighthouse Inc. will then take that directive with the information to control the user's lights and send the confirmation back to Alexa. So on the left-hand side is a sample directive that Alexa may send to Lighthouse Inc. You can see that this payload directive includes information such as the hue, saturation, and brightness, which is based on the corresponding values for the color blue that the user was trying to change to. Lighthouse Inc. receives the set color directive and then sends a set color response event back to Alexa once the device has changed, and includes the confirmation of the updated values for that device. And on the right-hand side, you'll see that hue, saturation, brightness confirmation. So common questions that Lighthouse Inc. may ask is, am I sending the right response back to Alexa? Lighthouse Inc. can use the smart home validation schemas to validate the responses, and these schemas can be found on the Alexa Smart Home GitHub. These JSON schemas provided are language agnostic and can be used with any JSON validator. In the Alexa GitHub, we provide a link to free online JSON validators that Lighthouse Inc. can use. And in this example on the screen, Lighthouse Inc. can use this JSON validator to copy the schema file that they found on the Alexa GitHub on the left-hand side and copy any response that they're sending back to Alexa on the right-hand side, as you see in the input JSON schema. They can find these responses in their Lambda log. In this example, you can see that the JSON schema validator has uncovered one error. On line 5, you'll see that there is a required properties that is missing from the payload version, indicating that Lighthouse Inc. needs to add a field indicating the payload version. So common errors that we often see in the response payloads is that the response is missing the required attributes, such as the payload version that we saw earlier. Other common errors that we see include incorrect data types. For example, Alexa may be expecting a string, but received an integer back from the response, or may have expected a Boolean, but got a string, such as true false, when the true false should have been in quotes. Lastly, another example is Alexa often expects a Boolean, but may get an integer. Now that Lighthouse Inc. has validated their responses, I'm going to hand it over to Sumit Dang to talk through how to debug and test your skill.
Thank you, Diane. Hi everyone, I am Sumit Dang and I'm a software development manager on Alexa Smart Home team. Before we start debugging a smart home skill, let's quickly revisit a high-level user interaction with the device. Here, when user says, Alexa, turn the light to blue, Amazon Cloud processes that request and triggers set color directive for Lighthouse Sync. Lighthouse Sync will take the information from set color directive and control the device in their cloud. Once done, Lighthouse Sync will send a response back to Alexa, and Alexa will then respond to the user. Now, there are additional ways to control a smart home device. User can use a native mobile app provided by Lighthouse Inc. or can just physically interact using a manual switch. In those scenarios, request directly goes to Lighthouse Inc. Lighthouse Inc. control the device in their cloud and responds to the user. As this request was not initiated by Alexa backend system will have no clue about the device state change. In order to update the device state in Alexa backend, Lighthouse Inc. needs to send a change report, also known as proactive state update. Similar asynchronous events should be sent in form of add or update report and delete report in cases when user adds, renames, or removes a device from his account. All these asynchronous events can be validated using JSON schema validator as Diane demonstrated earlier. Let's assume Lighthouse Inc. has now completed their implementation for color controller capability. As part of their initial test, they can verify differentiable colors like blue and red with visual verification. But in case of similar looking colors like salmon and orange, they will need a more effective and decisive tool to verify if the device is changing to the right color. Let's say they meet the two prerequisites for using state reporting test tool. One, they are sending change reports to Alexa. And second, they have been granted access by Amazon to use the tool. In order to request access, you can use the link as given in the slide. With that situation, let's see how Lighthouse Inc. can use state reporting test tool for their use case. Once Lighthouse Inc. has access to state reporting test tool, they can go to alexa.amazon.com, pick Smart Home and Devices. And here, Lighthouse Inc. will be able to see all the devices in their account. For this demo, we will use Light 001. For now, we have power state set to off and color properties set to white. To trigger interactions with Light 001, Lighthouse Inc. needs to go to developer.amazon.com, Developer Console, and pick their skill. On this page, they can click Test tab. To keep this demo simple, let's uncheck all these checkboxes. And here, Lighthouse Inc. can use Alexa Simulator mic option or type in the text box to control the device. For simplicity, we are going with the text option. Let's turn on Light 001. Once we get a confirmation from Alexa, we can go back to alexa.amazon.com, refresh the page, and we should be able to see power state of light 001 to be turned on. This was a basic example of how Lighthouse Inc. can change and validate state of the device. Now let's validate use case for color controller capability by setting light 001 to orange this time. Once we get a confirmation from Alexa, we can go back to alexa.amazon.com and refresh the page again. This time, the power state still says on and the color property is set to orange. Hue, saturation and brightness values are updated as first line item here. To demo the effectiveness of this tool, let's pick up another color which is similar to orange. So set light 001 to salmon this time. Once we get a confirmation from Alexa, going back on alexa.amazon.com, and before we refresh, please take a note of hue, saturation and brightness values as 39, 1 and 1 for color orange. But once we refresh, the color should be picking up as salmon and hue, saturation, brightness values are 17.52 and 1. To learn more about this tool, search for State Reporting Test Tool on developer.amazon.com. At this point, I hope we all agree that State Reporting Test Tool can help skilled developers to effectively verify device states by just sending change reports. Change report payload can be verified using JSON schema validator, as we already discussed. But what if there is a processing error with the change report itself? So the question for Lighthouse Inc. here is, how do I debug asynchronous events? For that use case, Lighthouse Inc. can use Smart Home Live Debugger to see the JSON payload for all reported asynchronous events as perceived by Alexa. To use Smart Home Live Debugger, Lighthouse Inc. needs to go to developer.amazon.com, Alexa, and go to Developer Console. They can pick their skill and click Test tab. Let's free up some space and select Device Log. Also, toggle on to create a debug session with Smart Home Live Debugger. To keep this demo simple, let's debug asynchronous change report events. Lighthouse Inc. can use same steps to debug add or update reports and delete reports by adding, modifying, and deleting devices from their Alexa account. Now, to generate change report events, we can use Lighthouse Inc.'s native mobile app or a physical interaction to control the device. First, I am going to turn off and turn back on this device manually. Here, we can see a change report first for turn off light and then for turn on light coming in. Let's take a closer look at the details of these reported events. Once we click a reported event, we will see a JSON representation of incoming change report for physical interaction for turn off light in this case. This report contains information for name, which is change report in this case, payload version, endpoint ID information, type of interaction, physical interaction in this case, and the change details payload. Same set of information should be available for our second interaction while turning on the device. This was a basic example of how Lighthouse Inc. can generate and validate asynchronous events reported by their skill. Next, I'm using the same app and changing the color to blue. We should have another change report coming in, and detailed payload will have information for hue, saturation, brightness set to 240, 1 and 1. This way, Lighthouse Inc. can control the power and color attributes of this bulb using a physical interaction or a native app, and use Smart Home Live Debugger to debug reported events. Lastly, let's turn off the light bulb. These were a set of successful tests for Smart Home Live Debugger, where we have seen expected events coming in. All these reported events contain a message ID. This message ID serves as a unique transaction ID which is common between Lighthouse Inc. and Alexa. In case of processing errors, Smart Home Live Debugger will show an actionable error message along with message ID. Lighthouse Inc. can use the given message ID to further debug the reported error in their backend systems. To learn more about this tool, search for Smart Home Live Debugger on developer.amazon.com. Now, let's continue with our case study of Lighthouse Inc. Lighthouse Inc. now implemented brightness controller along with color controller. So they have two capabilities implemented, and now they want to see if these two implemented capabilities are interacting correctly. They want to make sure that if we are changing the brightness of the bulb, it should not change the color, and if we are changing the color of the bulb, it should not change the brightness. For that use case, they can use Smart Home Evaluation APIs. Smart Home Evaluation APIs provide predefined test plans for lighting and thermostat capabilities. Lighthouse Inc. can use these APIs to run a set of automated tests against their skill. Let's see how Lighthouse Inc. can use these APIs using Ask CLI. At this point, Lighthouse Inc. should have information about their skill ID and endpoint ID, also known as device ID. But they still need to get test plan ID before starting a test run. They can use List the Smart Home Capability Test Plans API to get the list of all available predefined test plans. Here, in the response payload, every item in the list will hold information for a single test plan, with ID attribute as unique identifier for the test plan name. Also, as mentioned in the test plan description, color controller test plan will also validate turn off, turn on, set color, set brightness directives during the test run. Once Lighthouse Inc. decide on the test plan they want to use, Lighthouse Inc. can use Create Smart Home Capability Evaluation API to start a test run by providing skill ID, endpoint ID, and test plan ID. Response payload will have evaluation ID as a unique identifier for this test run. At any point in time, Lighthouse Inc. can use List Smart Home Capability Evaluations API to get the list of all past test runs for the given skill ID. Here, in the response payload, every item in the list will hold information for a single test run, with details around test run ID, status, start, and end timestamps. For a given evaluation ID, Lighthouse Inc. can use Get Smart Home Capability Evaluation API to fetch top-level information and status of a smart home capability evaluation. Metrics object in the response payload will hold number of total test cases, past test cases, and failed test cases for this test run. And finally, for a given evaluation ID, Lighthouse Inc. can use Get Smart Home Capability Evaluation Results. This API will help them to fetch detailed report of a smart home capability evaluation. And in this case, the response payload will have execution details of each test case. Next, let's see how Lighthouse Inc. can debug a failed test case. Here, in the test case status, if the test case status says error, that means given test case went to error state, like the device was offline before even execution. In case test case status says failed, that means it was able to execute successfully, but actual results were not matching to the expected results. Let's see how we can read a test case. Directives section of the test case defines the requested action. Here it says set color with hue equals to 120, saturation as 1, and brightness as 1. Expected state shows that the bulb should turn on and the color should be set to the given hue, saturation, and brightness values. Actual state shows the bulb was off after the test case execution. Now, in order to debug this test case further, we need to find the same test case in color controller test plan. All supported test plans are available in public GitHub. In the right-hand section, for test case from the test plan, initial setup section confirms that the test case will turn off the bulb first by sending turn off directive. Next, it will execute set color with hue, saturation, and brightness values as 120, 1, and 1. And test case expects the bulb to turn on and set the color using these values. This means, as per the recommended behavior, set color directive implementation should be able to turn on the bulb and then set the given color. But as per the test case execution results on the left, this bulb did not turn on with set color directive. The power state on the left hand side says off, while the power state on the right hand side still says on. Hence, Lighthouse Inc. should fix this problem and execute turn on directive before set color. That should turn on the light bulb even if it's off. This was one of the examples where Lighthouse Inc. was able to debug an issue with their color controller implementation. You can imagine this tool being useful for several other similar test cases. To learn more about these APIs, search for Smart Home Evaluation API on developer.amazon.com. With that, I'm going to hand it back over to Diane to talk about how Lighthouse Inc. can manage the performance of their skill.
Thank you, Sumit. Now that Lighthouse Inc. has validated and tested the responses, we're going to walk through how Lighthouse Inc. can manage their skill performance. We're going to assume that Lighthouse Inc. has certified and published their Alexa smart home skill and is now being used by their users. The Alexa Developer Console provides an analytics page for Lighthouse Inc. to understand what's working well and opportunities for improvement. So on the Analytics tab of the Alexa Developer Console, Lighthouse Inc. will be able to see a summary of metrics that includes number of utterances, number of customers, and actions that have been taken on their skill. They will also see a operational metrics section for smart home skills. To see how Lighthouse Inc.'s skill is performing, we're going to take a deeper look at these operational metrics for capability directives. The latency is the time that Alexa receives your response from Lighthouse Inc.'s skill after Alexa sends a response to Lighthouse Inc. So in this example, we see that Lighthouse Inc. has an average P90 latency of about 162 milliseconds. Generally, we aim to have a P90 latency of 600 milliseconds or less. The success rate indicates the total number of successful responses Alexa receives from your skill divided by the total number of requests that Alexa has sent. In this example, in the blue line, we see that the success rate is generally 100% for Lighthouse Inc. But we see on May 25th that the success rate dropped to 89%. When working with our partners, we typically aim to have a success rate of 90% or higher. And lastly, on the analytics page, you'll also see a change report accuracy rate. When the state of a device changes for any reason, such as a user turning on a light, Lighthouse Inc. can actually send a report back to Alexa in a change report, or also known as a proactive state update, so that Alexa can communicate these changes to the user. This change report rate shows the accuracy rate of these events. And in this example, the accuracy rate of the change reports is about 94.7%. We generally aim to have a change report accuracy rate of 95% or higher. And now that we've walked through some of the metrics available on the Alexa Developer Console, we're going to hear from Philips Hue to see how they've managed their skill and made improvements to their skill throughout the last 5 years. I'm going to turn it over to George now.
Hi, my name's George Yianni, and I'm the CTO and one of the founders of Philips Hue. And I want to tell you a little bit about our journey for how we made Philips Hue and Alexa work together over the last years. Now, Philips Hue is one of the leading lighting systems in the world. We're actually one of the few products to work with Amazon Alexa when they first launched. We have over 200 different kinds of smart product, ranging from a broad range of different light bulbs towards integrated fixtures, sensors, switches, but even things like AV gear, like our sync box, which synchronizes any content on your TV screen towards your lights. Now, when we set out building our smart home skill, how we would integrate with Amazon Alexa, there were a few key things that we held dear to us. The first was something that's pretty core to the Philips Hue vision, which is that we can make everyday moments more magical and extraordinary with the right lighting. But to do that, we have to make lighting really intuitive. You shouldn't have yet another thing to control. So it's all about having rich experiences from simple interactions. And voice fits extremely well into that, because with a very short utterance, you can access a breadth of different functionality, a breadth of different lighting ambiances inside your home, but also have those simple interactions control more than just lighting in your home, do something really magical. The next thing is all about what we called time to light. Now, we all know artificial lighting. We've all had it in our homes since we can remember, and we have been trained to expect a few things. When we press a button in our home, we expect the light to turn on instantaneously. So we've been trained to actually expect that kind of response. With smart lighting, actually, we should not be worse than the dumb product. So we put a lot of effort into making sure that the time until the light turns on from your interaction is as short as possible. That's always a key goal. And the final thing in the same vein is really reliability at scale. You have a lot of light points in your home, and we have many consumers who have tens. I think the record is about 700 light points in their home. And interacting with those has to be reliable all the time, because that's what you expect from the lighting you had in your home before. If it doesn't work well enough in whatever we build, you're going to stop using it. So that's always been a key thing for us when you're at scale in terms of number of light points in a home, but also scale around the world. So let's have a look what turning on a light bulb looks like in 2020. As you can see, it's pretty complex. It involves multiple clouds interacting with each other. And what we started with in 2017 has actually got more complex in 2020 as we've added functionality and improved performance. And I want to take you through a few of the design decisions that led us through this journey. Now, first, let's talk about time to light. When we first built Philips Hue, actually, cloud latency was not something that was very important for us. We built that functionality so that you could have the peace of mind of checking in on your home when you were at work, seeing if someone had come home or not, you hadn't forgot to turn off the lights. And these are all use cases where actually latency is not important because you can't see the light. Now, all that changed when Amazon Alexa came on the scene. And actually, we were talking to things in our home which were then via a cloud turning on the lights. So suddenly it became absolutely critical. And the infrastructure that we built with from one of our suppliers, where we would kick a bridge and then the bridge would start polling, could deliver around 2 seconds of latency. And like I said, we expect instantaneous. Our studies show if it's less than 400 milliseconds, you're okay. Above that, you start having to warn consumers it's going to take a long time and it feels slow. So we looked, what are the technologies out there to actually improve that latency, get us below this 400 millisecond goal. And we actually didn't find anything off the shelf that was really appropriate at the time. A lot of solutions really focused not on measuring the end-to-end latency, the time that the message really gets into the home and the action is taken, but measuring time to changing shadow states, which was not actually important. And so we actually built something custom in the end, where we chose what we thought would have the ultimate lowest long-term latency. And that's by actually maintaining a WebSocket connection permanently from every home towards a server in our cloud backend, so that it's always there ready to push a message down when a control command comes in. And so that's what we went and built, and actually it has served the purpose well. We're able in many parts of the world to have that latency well below 400 milliseconds. And we keep finding ways to trim a few more tens of milliseconds off that to get closer towards our goals. Now, it was not an easy experience, especially when scaling. You can imagine if you have to have servers which can reliably 24/7 maintain a WebSocket to millions of homes geographically distributed around the world, there's going to be some challenges. But as we stand now, we've worked through most of those and we have a solution we're pretty happy with. Next, let's talk about experimentation. When Amazon came and told us about their new proactive state capability, first of all, we were pretty excited. We like to have simple interactions, create rich experiences, and proactive state lets us, for example, have our motion sensors not just turn on the lights, but also do other things inside the home, maybe control your blinds, set the thermostat temperature, which is a pretty powerful use case. You walk in and all this stuff happens inside your home. So we're pretty excited about what it could bring, but we also saw it as an opportunity to try something new. So when we followed the recommendations and we built a new Lambda to handle the proactive events, we decided to try building it in Go instead of Node.js. And we found that actually a great experience. We found our code could be more maintainable, easier to test, and it actually executed a lot faster with lower memory machines. So we were pretty happy with that. So as we started scaling that up, we were feeling pretty confident, but we actually ran quite quickly into performance bottlenecks of the Lambda system, where actually we couldn't ramp up the Lambda instances fast enough. You can imagine that when we're sending all of these events towards Amazon, there are certain peaks in the day. And as it turns out, most of our consumers, when they set schedules, they do it on the hour. So every hour, suddenly all of these lights change, and that creates a flood of events which maybe need an action that happens immediately off them. And we just couldn't ramp up Lambdas fast enough. So we quickly pivoted the design and rebuilt it in Elastic Beanstalk with a dedicated instance that we could dimension up front for these peaks, and that solved the problem. Now back to Go, like I said, we found it was actually quite a good solution. So we actually then went and ported everything over towards Go, and that actually reduced the memory consumption of our instances, the runtime, to such a level that we more than halved our cost while reducing latency. So this experiment that we did on an off chance was actually worked really well for us. It's important to keep experimenting when you have the opportunity. So what's next? We've done a lot of things tweaking in the system to get latencies down, reliabilities up. In the last months, we found maybe 100 milliseconds of extra latency through some optimizations in the WebSocket pipeline. We've tried regionalizing not only our Amazon skills, which we now have 14 of around the world, but also our API gateway, which surprisingly did not have a big impact. But the real big goal we're working towards now is full regionalization. We need to have servers closer towards people so that everywhere in the world we can enjoy the same latencies we have in the parts of the world where we have servers. So let's have a look back at some of the things we've talked about. I think the first thing to realize is, the complexity to turn on a light bulb 2020 is pretty high. And actually the real end solution to get the best possible latencies is actually to avoid the clouds altogether and actually keep things in the home as much as possible. And this is something that we also look for solutions of, also in the case of Amazon Alexa. Another thing that was very important to us was keep the focus on full chain metrics, and don't be tricked into looking at the latency to update your shadow state. Really look at the latency to turn on the light bulb or your equivalent of the light bulb, and it leads to very different design decisions. And I think finally, by continuously experimenting at scale, you will find problems, but you will also find opportunities to improve. And so when you are building something new or something different, take the opportunity to try doing it in a slightly different way, and maybe you'll find something that helps you. Thank you. I hope you enjoyed the rest of the talks, and I will pass back now so you can hear more about the various tools that you have available to you. Thank you.
Thank you, George. As we close out this session, let us reiterate on the key tools that you can use during your development and management of your smart home skill. During implementation, you can use the Alexa Smart Home JSON validator to validate the responses you send back to Alexa. These schemas can be found on the Alexa Smart Home GitHub. For debugging, we have two tools available for you: the State Reporting tool, which can be used to verify the states of all your smart home devices, and the Smart Home Live Debugger, which shows the events that Alexa receives from your skill in real time and any associated errors. For testing, you can use a Smart Home Evaluation API, which can be used for integration and regression testing as you build out new capabilities. And lastly, for managing your skill, go to the Operational Analytics page on the Alexa Developer Console, which provides information about your skill and its usage. You can find these tools by searching on developer.amazon.com. Finally, we want to thank George Yianni for joining us from Philips Hue and speaking to us today. And we also want to thank you for coming here in this session.